Are you a JavaScript developer interested in learning Go? Then you've come to the right place. If you don't know much about Go, it's a programming language developed by Google. It's statically typed, automatic garbage collection. It's extremely fast. It compiles fast, and it's used in a lot of interesting applications, some of which you may have used in the JavaScript world. Turbo Repo, Hugo, ESBuild, Kubernetes, Terraform. All of these tools are built in Go. So in this video, I want to show you how JavaScript and Go kind of compare. But by the end of it, my goal is that you can jump into a Go code base and understand what's going on and even write some code and be productive. All right, so the first thing let's talk about is getting set up with Go. So I recommend just going to Go's website to download Go. Once you download Go, you're gonna have access to the Go tool. The Go tool is a powerful tool that will let you interact with the programming language. It will let you compile and execute your code, run tests, install dependencies, even to format and lint your code. Once you've installed Go, you should be able to access the Go tool from your command line. So I'm just going to type in Go here, and you can see all of the commands that are available to you here. So if we want to know the version of Go we're using, we can say Go version. And you can see here we're using Go 1.19. All right, so the next thing I'm going to do here is just set up a project. I'm just going to make a directory. I'll call it YouTube Hello, and let's just jump into that directory. And then the first thing we're going to do here is similar to in JavaScript when you say npm init and it creates a package.json file. We're going to say go mod init, and then we're going to name our module, usually the name of your project. We'll just call it YouTube Go tutorial. All right, so as you can see here, we've got the Go mod file, and this is what it looks like. You can see the Go version is listed here, and here is the project that we gave it. So anytime you install a dependency, it's going to show up here. So for example, I'll install the UUID library by Google, and I'm going to say go get, and then we're going to download it from GitHub. And it's just going to be Google's UUID library. And then now when we look here, we can see we are using this UUID library. And you can see the version number here is printed as well. All right, so now that we've set up our Go project, let's write a simple program. In good computer science tradition, we will write a hello world app. So all executable programs need to be inside of a main package. So I'm going to create a file just called main.go. The first statement we're going to use in a Go file is what package it is, and we're going to call this the main package. All right, so then we could just create a main function here, and we're just going to print hello world, and we could do that simply by using the built-in command print line. And we'll say hello world. So at this point, we can go ahead and use the Go tool to compile and run this program all in one step. So we're going to say go run main.go, and boom, there you go, hello world. All right, so the next thing I want to discuss is how Go projects are usually structured in the real world. This isn't a requirement in Go projects, and there will be some variability from project to project. But I have seen this project structure show up quite a bit, so it could be useful to understand this general pattern. We would have a command directory, and everything in this command directory here would be all of our executable programs. So everything with the package main and a main function would go in this command directory. So we could move our Hello World app to command. And so then the next thing that you'll commonly see is a package directory. And so this is where all of the application code would live. So for example, like if we were doing a blogging application, We'd have our package directory, and then you might have more subcomponents within that package directory. So for example, you might have a package/auth, like a common utility library. You might have, your post library, and you might have, let's say, like a user library. And then inside of each one of these, you'd have your package logic, essentially. So you might have, for example, like in the auth directory, you might have like auth.go. And then also tests in Go projects are usually co-located with the implementation file. So you would usually see something like auth_test.go. And the underscore is actually a convention that is used by the Go tool. When you say Go test, the Go test tool will search your code for all the files with underscore test. So this is actually not just a personal preference thing here. This is actually a convention that is used by the Go tool to pick up what is a test or not. So then up here, you can kind of see how this might be structured in a blogging application. And you got your different modules here. And then each one of these files, it would be in package auth or package common, package post, or package user, for example. So again, this project structure is not a requirement. You could have all of your files at the root directory if you wanted, but this is a convention that is used quite a bit in some larger Go projects. All right, so the next thing I want to discuss with you is how to export code from different files. The way they do it in Go is they actually capitalize the function or the variable that you want exported. And I'll show you an example here. I'm going to create a new package, and I'm going to call it myMath. And the reason why I'm calling it myMath is because the standard library actually includes a math module, so I don't want to conflict with that library. But this is going to be a simple package, and we're going to have a module called arithmetic. So, of course, this is going to be in package myMath. And so if I want to export a add function, the way I would do it is by capitalizing the name of the function. So let me show you what I'm talking about here. So we want to do capital add, and it's going to take an X and a Y integer, and it's going to return an integer, okay? And so now if I create a my science directory here, and don't ask why I'm naming it science, just sounded right to me. And I'm going to create a sum.go. And I just want to show what this would look like to import this add function. Of course, this is package myScience. And I'm going to create a sum function. And it is going to take a list of integers and return the sum. And this is how you would do it, in the real world. But I want to show you how we can use our add function. So I'm going to say equals and then myMath.add. And there you go. You can see we're importing from our YouTube Go tutorial module, and we are getting it from the myMath package. And you can see here we are using the package name dot the exported function name, and of course we can pass in our arguments. And so that's what it looks like to export code and import it from outside of a package. So let me go back to arithmetic.go. If you wanted to create a function that is hidden from the outside world or hidden from packages outside of myMath, what we would do is not capitalize the function, and we would just say, for example, we could say subtract like that, and you can see subtract is not capitalized, so we will not be able to import this from any other package outside of myMath. So let me show you what I'm talking about here. So I'm gonna jump over to sum.go, and I'm going to try to go to my math, and you can see the only option they're giving me here is the add function. We cannot use subtract because it's not exported. It is package private. Now that's an important thing to remember. It is package private. I can go to my math package, for example, and I will just create an arbitrary foo.go, and I'll put it in my math package, and I will create just an arbitrary function. Doesn't really matter. I just want to show here that we can use subtract here. So subtract, even though it's not exported from the package, it is available from files outside of arithmetic.go. So if you did want to make a function that's truly private, so the way that you would do that in Go is with a function closure. So that function would only be accessible from within the outer function. So if arbitrarily we wanted to print results, then we can define a function closure, and you can see I'm using this :equal here. This is how we assign variables, and we can assign a function to this variable that prints the result. I don't need two variables here. I'll just do it with one variable. Now, here's another thing. This x is shadowing this outer function x, and that's usually a bad idea. So I will just call that z. And I'm going to assign a new variable, call it results, x plus y. And then see here, we will print the result and return it. It's very arbitrary. I know this is not anything that would be very useful in the real world, but I just want to show how you can create a function closure, because this function is not accessible from anywhere outside of add. So I can't be in subtract, for example, and access the print result function. So those are three different ways to export or hide functions in Go. And again, to export it, we just capitalize it. To keep it package private, we just not capitalize it. And if you want something that is truly, truly private, you could do it with a function closure. I just want to show you kind of the basic control flows that you can do in Go. So in Go, we have if statements. And as you can see, we don't need parentheses. You can have parentheses, but they are redundant and they're bad style. But if you have a complex Boolean condition, it can be helpful to have parentheses to understand a little clearer how the order of operations are. And of course, you could also do for loops. And again, no parentheses around here. Now, one thing to notice here, though, about :equal is if we assign a value using the :equal, that's the initial declaration. We can't reassign a variable with :equal. So for example, if I say x :equals 5, I can't also say x :equals 6. You can see here, we're getting an error that's saying no new variables on the left side of :equals. So this won't compile. And I can show you that here. I'll say go run command main.go, and we can see x declared but not used. That's another compile error. You can't not use a variable, and then no new variables on the left side of :equal. So if you want to reassign x, you would just do that with the equal sign. So that's just a little something to note and something that you kind of have to get used to coming from JavaScript. So also in Go, there's no while loops. We use the for loop for pretty much everything. And the way you would write it here is like this. So you would just say for, and then you would just put the condition right here. And this is effectively a while loop. And you can see here, again, we're doing the assignment here with the :equal, and then the reassignment here without the :equal. And then if you wanted a infinite loop, you would just say for. And that is your infinite loop. All right, so the next thing I'll show you here is the for range loop. You can see I am assigning this array here to values 1, 2, 3, 4, and 5. And then we're using this range keyword here. And then this lets us iterate over each element in the array, which in Go, they're actually called slices. But effectively, they're arrays, and that's how you can think of them. As you can see here, this range of nums is being assigned to 2 values here. Okay, the first value is this underscore, and then the second value is this, what we're calling in. Okay, this underscore is telling the Go compiler, hey, I do not care about this value. I am not going to use this value. Remember here, when we tried to compile that old program, remember it got mad because it said X declared but not used? If we were to assign this to something and not use it, it won't compile. So this tells the compiler, hey, we know this is returning something. We don't care. We're not using it. So we assign it to this special blank identifier. However, this value that is returned by range of nums is the index of the array. Since this program, we don't care about the index of the array, we're using the blank identifier. The second value is the value of the array, which we're calling in here. And just like in JavaScript, we have continue statements and break statements. All right, so then the next thing I want to show you is the switch statement. Very similar to JavaScript, we have a switch statement and kind of interesting formatting, but this is the preferred way to format switch statements, is to not indent the cases. This is how the Go format tool will do it. But as you can see, it's pretty similar to the way they work in JavaScript. However, there's one key difference here, is we do not need to write a break statement at the end of each case. It is smart enough to know if it enters into a case, then that's the only case you care about. However, if you do want it to fall through to the next case, Go has a fall through keyword, which would then let it go to the next case down. The next thing I want to show you is some of the common data structures you're going to use in a Go application. And those are slices, which we've already looked at, maps, and structs. So slices work similar to JavaScript arrays. Here we're declaring a empty slice. This is another way here you can declare variables in Go. You can use the var keyword, give it the name, and say what type it is. This is how you add elements to an array in Go. You use the append keyword, you give it the array you want to add to, and you give it the element you want to add. Then you would reassign that value there. And then there's the length keyword or len keyword, and that would give you the length of the array. So I'm gonna just run this program right from IntelliJ, and we can see here that the length is, of course, 10, and that is what's printed. Go doesn't have a rich set of array methods such as map, reduce, filter, and it's up to you, the developer, to write for loops and do that functionality by hand. But that may change because in Go 1.18, they did release generics, which theoretically would pave the way for more functional style methods such as map and filter and so forth. So the next type of data structure I'm going to show you here is the map. So here we are statically declaring a map of length 3. And here you can see we have the keys here and the values here. And we access that map similar to how you would access like an array of an element, but then you just give it the key here. So another thing you might be accustomed to using in JavaScript are sets. In Go, we don't have sets per se, but we use maps to represent sets in Go. And the way that we would do it here is by mapping a whatever key type. It can be a string, it can be an int, doesn't matter as long as it's serializable. And we would just map that to a bool and just assign it to true everywhere. And then you can just access your set that way. So that's one way you can represent a set in Go. So another thing about Go maps to keep in mind is that they actually return two values when you access them here. And those two values are the value from the map and also this value called OK. Well, it's typically called OK. And this value is a indication of whether that key actually exists in the array or not. And the reason why this is important is because if a value, say a value foo, and if we access an element that does not exist in our map, then what's going to be returned is the 0 value for that data type. For an int, that 0 value is 0. For a Boolean, the 0 value is false. For a string, the 0 value is an empty string. And so that's what you would get if the field was not present. And so here you can see 4 is not present in here. So OK would return false, while the value coming from here would be 0. And I will run that for you here. So there you go. All right, so then the next thing to look at in Go is structs. And these are very, very similar to just objects in JavaScript. And here's how we would define a struct type. We say type, give it the name of the struct, and use the struct keyword, and then you would list out its properties right here. And so just like with functions, you can choose to capitalize the struct in order for it to be accessible outside of the package, or you could not capitalize it and the struct would be package private. And similar to fields. So if this person object is exported, if I'm outside of this package, then I would only be able to access name and age. I would not be able to access government ID because government ID is not exported from the person object. So here is how you would declare a person struct. You can see we're using the name of the struct, and then we just give it the list of key and values. And then similar to how a JavaScript object works, we can access properties on the struct using the dot notation. So I'll run this program so you can see how this looks. And you can see it prints John and age 30 here. So another cool thing about structs is you can assign methods to structs. So for example, I could give the person struct a method, say hello. And you can see here the first parameter on this method is the parameter p, which is a person. And you can kind of think of this as like the this keyword in JavaScript. Like if you're writing a class in JavaScript, you can say like this dot property equals whatever. It's very, very similar here. So this is kind of like the stateful this property. So when we create this person, we call him John, age 30. We can say p dot say hello. And when we run that, it'll say, hello, my name is John. So you might be thinking, wow, that's cool. And that it seems like Go is an object-oriented programming language. And I would say be careful there, because although you can assign methods to structs, and it does seem like something you could do in an object-oriented language, there's no concept of inheritance in Golang. However, you can use Go interfaces to achieve polymorphism. So for example, I can define a speaker interface, and I can give it a speak method. And then I can have a type dog struct, and the dog can have a name. And so then that dog could speak, right? And when we call that method, it will say, the name says wolf. And so we say that the dog struct implements the speaker interface. And similarly, we can define a person. You give it a name. And the person could also implement the speaker interface. And it can say, the name says hello. All right, so then we'll create a little test client here. We'll create a person named John, and you can see this here. In Go, you don't actually have to put in the name of the property, colon, the property. If you just assign the variables in the order that they're declared in the struct definition, you can just do it in line. However, if it was like age int, then you would have to define that here, and you couldn't like reverse order these and say like 80 here and then put the name here. So it's kind of up to you. I feel like it's a little more maintainable if you go ahead and just put the key there from personal experience. So we're gonna create a dog as well. We'll call it D, and then I'm gonna create a variable S, which is going to be a speaker. And I can assign both the person and the dog to S because they both implement the speaker interface. And notice that they're implementing it implicitly, not explicitly. Whereas in some language, you have to say that the type implements an interface. In Go, we actually don't have to do that. We can just implicitly implement the interface, and the compiler is smart enough to determine if that variable correctly implemented the interface. So I'm going to assign S to P. Then I can say s.speak. Then I'll assign S to D. And then I'll say s.speak. I will run this program here. And you can see here, we can get the kind of polymorphic effect happening here. All right, so then the next thing I want to discuss with you is error handling in Go, which is pretty unique actually in Go. So in JavaScript, for handling errors, you're probably used to throwing error objects and using try-catch blocks to handle them. In Go, it's a little bit different. So in Go, if a function could result in an error, the practice is to return that error as the last thing that it returns, and then let the caller decide what to do with the error. And so I think the intention here is that they want error handling in Go to be very intentional. So simple program here, and all it's doing is reading a data.csv file, and it's just going to print that to the console. So let's look into this read.csv file. You can see here we are opening that file, and you can see here also this opening of the file could result in an error. And so this open function returns both the file, it also returns an error. And so if there is no error, that error would be nil. If there is an error, it would not be nil. And in this case, the way we're going to decide to handle it is by essentially killing the program, log.fatal. And this is a function that is going to print this and then call os.exit with a status code of 1, which is basically just saying stop the program and indicate that there was an error. So if this cannot open the file, this returns a not nil error, and we will kill the program. Here's another new keyword to introduce you to, and this is the defer keyword. And the way this works in Go is this is basically saying, hey, close the file after this function returns. And so this is kind of similar to the finally keyword in a try-catch finally block in JavaScript, where in a try-catch finally, anything you put in that finally statement will be executed after the return statement. So it's a very similar concept here. We're just saying we know we want to close this, but we want to just close it after the return statement. And the reason why the first statement is convenient is if you have a function that has many places where it could return from the function, then you only have to define it in one place as opposed to remembering to call this cleanup function in every single place that it could return. So it's just a convenience there. So then we're creating a CSV reader. We're reading all of the file. And again, reading the file can result in an error. So similar thing here, if that error is not nil, we will kill the program with an error message. And then otherwise, we'll just return the record. So this is a pretty common pattern you'll see in Go. And this is how we handle errors in Go. So in a lot of Go programs, you'll see, a function called. The function could return an error, and you'll see something like if error does not equal nil, or if there is an error, then do something with it. A lot of times your function will probably just propagate the error up further. So it's like possible that we could have set this function to also return an error. And if this error was not nil, then we could just return that error. So it's kind of up to you. And that's kind of is what's nice about Go is you have to really be very intentional about how you handle errors. Now, there is another special keyword here, and here's a different program also showing you some new library functions as well. And so what this program is going to do here is accept a command line argument. And for the sake of an example, the argument is going to be a regular expression. We're just going to trim the space off the left and right side of that argument that's passed in. And what we got here is what looks like some randomness. We are randomly selecting a path here, but each branch is going to be effectively the same type of thing. So here we are calling the regular expression function called compile. It basically return a regular expression object that we can use to do regular expressions. But if there's an error, it means that it was not a valid regular expression. If there is an error, if it's not nil, then we'll use the panic keyword. And a panic, you can think of a panic as like a runtime error. It's basically like a developer error, for example. So you really don't want like a production app to panic, or if it does panic, it really means that there's a bug. In this else branch, what we have is this must compile alternate function here. And this is very similar to compile, except for this only returns a regular expression, doesn't return an error. If it cannot compile, it will panic internally. I'll go into this function. You can see here, they actually call the compile function. And if it is not nil, then they will panic here. Okay. So this is a pretty common idiom, actually. You'll see this a lot in the standard library. You'll have like a function, and then you'll have like must that function. And the must variant is a version that will panic if it can't compile it. So kind of two different ways to show you kind of the same thing, and they give you another tool in your tool belt. Also in Go, we can have pointers. Unlike this here, what we'll do is prefix it here with the ampersand, and then that creates a pointer. Once you've got a pointer, you could pretty much use it the same way as if it wasn't a pointer to a person. A lot of times people will use a pointer value if they want the value to be nil. If it's not a pointer, the person P will not be nil ever. Let me show you an example. So like if I had like a print person name, it took a person and it printed the name like this. If it was not a pointer, then you would have to give it a person object, right? Like that. A lot of times people will use a pointer, and the way that we will define a pointer is we'll use the star symbol here. And that says that we're looking for a person pointer. If I wanted to define a variable P and I wanted it to be a pointer to a person, then I would prefix the person declaration with an ampersand here, okay? And then when I pass it in here, we can see that it is happy with that, and it can print that person using the person pointer. But the thing here with the pointer is that the P value can be nullable. So I can say like if P equals nil, then don't do anything, right? Because if I pass in nil here, then this won't kill the program. But if it is nil here, then this is going to panic because there's no first name on nil. So if I run this here, we can see, and then it's mad because I didn't use that variable, so it didn't compile. But right here, we can see that it panicked, a runtime error, invalid memory address or nil pointer dereference. And that's because we didn't give it a valid person pointer here. If I give it P here, then we can run this and it should print the name here. So why would we use a pointer anyway? So pointers can be useful because if we don't use a pointer, Go will actually copy the value. If this was a person object, and if I pass in P here like this, and then let me get rid of this because, again, if it's not a pointer, it can't be nil. So if I go in here and I say like P dot last name is Joe Smith. All right, so it's not a pointer. So what would you expect this to print out? So again, we create a person. The person's name is Joe Doe. We call this function print person name, pass in P. We assign the last name to Smith, and then we print that. Then we come back out of that function, and then we print it again here. So what would you expect that to return? So let's run it and find out. And you can see here the print person name prints Joe Smith, and then the outer function prints the original first name and last name. And the reason it did that is because when we pass in P here, it makes a copy of this person. So it doesn't affect this person out here. But if we used a pointer instead, like that, and then if I gave it a pointer to this person here, now when I assign the last name to Smith, it's going to affect this P here because we've given it a pointer here. So now when I run this, we can see Joe Smith is printed twice. That's because we gave it a pointer. So there is one thing I want to show you that really makes Go a special programming language, and that is its way to handle concurrency. Two techniques in Go to handle concurrency, that is Goroutines and channels. And so the way we do a Go routine here is with the keyword Go. If we have this function say, and it waits some time, it sleeps for a little bit, and then prints out a string, then we could essentially run this in two Go routines by saying Go and then sending off this Go routine and then sending it off here. And one thing to keep in mind is that the main function, or any Go program for that matter, runs as a Go routine. So even though I'm only using the Go keyword once, this is actually running in two Go routines. The first Go routine is just the main function. The second Go routine is when we spin up this Go routine here. And so when we run this function, the output of hello world should be interleaved because they're both running concurrently. So let me run that and show you what I mean. And so here you can see the output is intermixed, not one after another. And another thing is that this output is not deterministic. I could run it again and we might get different results. We might get the same, but the point is the output here is not deterministic. So that's great, but we often want to be able to use the results of functions that are running in parallel. And the way we do that is with channels. The way we did it in JavaScript is, you might, if you wanted to run async functions, you might call promise.all. and give it a list of all those asynchronous functions. So we can do something similar in Go, but the way to set it up is a bit different. And the way we set it up is with channels. So I'm going to introduce another construct in Go, and that is the channel. And you can see that this here, this variable C is a channel that stores an int. And so a channel can be written to and it can be read from. And the way we write to a channel is with this left arrow symbol. And the way we read from the channel is with, well, also the left arrow, but it's on the left side. And don't worry about trying to remember that. Just kind of think of it like literally an arrow. Like what we're doing here is we are putting some into the channel, right? So the arrow is like the pointer of like, where is this sum going? And then here we are putting what's in the channel into X, or putting what's into the channel into Y. That is how we would coordinate or capture values that are running asynchronously. So again, we have this sum function that's just taking a sum of integers. And here we are constructing a new channel, and we're doing that with the make keyword. So the make keyword is how we can create a channel. And by the way, we can also use the make keyword to create slices and maps. But here we're showing how to use make to create a channel, which we're calling C. And here we're running both of these functions in parallel. When you read from this channel, it's going to block until that channel has a value. So when you see this left arrow where we're reading from this channel and we're saying like, I need the value of this channel to be assigned to X, that means that it will block until this channel is written to. If it doesn't have a value in the channel, it will not continue execution. This is kind of like running a promise out all in JavaScript. We are running this asynchronously. We're running this asynchronously, as you can see, because we're using the go keyword and calling this function. And here we are doing the await by blocking on this channel. And so once we get the X and the Y, we will print the sum of those. And so let's see what that looks like. And so you can see we get -5, 17, and 12. And the reason why is we are giving it half of the list, and actually we're giving it the second half of the list in the first Go routine here, and the first half of the list in the second Go routine. And this is another special way that you can return sub lists. You can also do this with strings as well. But we can see like this is basically saying like, hey, I want everything up until the length divided by 2. So give me like half of it, the second half. If you wanted like just from the first index to the second half, that's how you would do it. But if you put nothing here, it's basically from the beginning of the list. And then here, this is starting at this index to the end of the list. Another little tool here that you can keep in mind. But yeah, so these are running in parallel. And so if I were to sleep for 1 second, just to simulate like a longer duration to calculate this, it should take roughly 1 second to execute the program because these are both running in parallel. And we will test that too by saying start time. And we'll start it at time.now. And I'm going to print the time since the start time. And it should be around 1 second still. Yeah, and so you can see here, it's about 1 second because these two methods or two Go routines are running in parallel. So quiz question. So how many Go routines make up this entire program? Think about that. If you said 2, that would be incorrect. And there are 2 Go routines right here, but remember also the main function runs in a Go routine as well. So this is actually being run in 3 Go routines. I would say you should have enough Go knowledge now that you could go into a Go code base and kind of start to understand what's going on and kind of some of the different control flows and structures there. Make sure to like and subscribe if you liked this. It gives me a signal that this is the kind of content you want more of. Thank you for watching, and I hope you write some incredible Go programs.